This is 8.1.4 complex conjugation. In complex conjugation, the complex conjugation is an operation. It operates on a complex number. So example, we are given z is a plus jb. The complex conjugate of z is denoted by z with a bar on top. This bar on top indicates that we are taking the complex conjugate of z. What changes? Well, you now see that complex conjugation is nothing more than the changing of the sign. For example, the original sign of the imaginary part is plus jb. Now it becomes minus jb. So let's have another example. If we are given that z is originally a minus jb, then the sign, originally minus, is now changed to plus. So complex conjugation simply changes the sign of the imaginary part. What about these two bars on top? It means that we take z, complex conjugate twice. And if we complex conjugate twice, we get back z. We'll now show some results of complex conjugation operation. So if z is equals to a plus jb, and the complex conjugate of z is therefore a minus jb, now we are going to add these two together. Well, what you realize is that when we add z and its complex conjugate, the real part adds, becomes 2a, and the imaginary part cancels. So z plus z conjugate is 2a. Or we can call it the 2 times the real part of z, since the real part of z is a. Similarly, z minus z bar. Let's see what we can do with this. So I write z equals to a plus jb minus z bar is equals to a minus jb. So a minus a becomes 0. And now plus jb minus minus means plus, so it's 2jb. Therefore, the answer is that z minus z bar is equals to 2jb, is 2j times the imaginary part of b, and the imaginary part of b is, imaginary part of z is b. In this last operation, z multiplying by z conjugate, well, if we write it in rectangular form, we are going to do the cross multiplication of all these terms. We'll get a squared plus b squared. You try it by yourself. You basically realize that the imaginary part cancels. If you actually do this in the polar form, it is much easier to understand. Let this represent z, and of course z bar is simply the same modulus but with a negative theta, where theta is the argument of z. So if we observe this and remember what happens in the multiplication in polar form, the modulus will now multiply with each other. So we have r modulus square, and theta will add. But since theta add with minus theta, it becomes 0. So basically, this converts a complex number, two complex number, into a real number, because there is no imaginary part. So what is r square? R square is simply a square plus b square, as we know in the Pythagoras theorem. Finally, let us try this operation. z1 times z2 bar, we say that it is equals to z1 bar times z2 bar. How do you prove this? Well, simply you use the polar form, because it's easier to take multiplication in the polar form. So it's r1 angle theta 1 for z1, r2 angle theta 2 for z2. All of them is conjugated. r1 times r2 brings it out. Since they are multiplying, the theta 1 adds to theta 2. The complex conjugate of this value simply changes the theta, so minus this theta. So this is z1 times z2 complex conjugate. If we do it individually, then we will now write R1 angle theta 1 bar, indicating that this is Z1 bar, and the second term is R2 angle theta 2 bar, indicating this is Z2 bar. We first remove the complex conjugate by putting the complex conjugate operation, or realizing the complex conjugate operation. So theta 1 becomes theta 1 becomes minus theta 1 for the complex conjugation. The magnitude remains unchanged. This is the same. The complex conjugate realizes minus theta 2 for R2. We now can multiply. R1 multiplied by R2, the modulus multiplies. The angle adds minus theta 1, adding with minus theta 2 is minus theta 1 minus theta 2. We bring the minus sign out, and then we have this. And this is exactly the same as this on the green side. And we see that Z1, Z2 bar is equals to Z1 bar times Z2 bar. We now continue with the complex conjugation, the geometric interpretation of complex conjugation. If we are given Z equals to 6 plus J4, the complex conjugate of Z simply changes the sign here. From plus becomes negative. What you realize is that it is nothing but projecting this phasor, this phasor or this vector across the horizontal plane to the other side. So this is one interpretation of complex conjugation. The length of the vector remains the change, but we are flipping the vector across the horizontal plane. The other way to think about complex conjugation is to consider the angle. Remember that if this is Z and we have the length and the angle, then Z bar is simply the same length, but the angle is now negative. So what does the negative angle means? Well, here is the positive angle theta, and here is the negative angle theta. So basically, it is also telling us the same story, that the phasor or the vector actually flips across the horizontal axis by the same amount of theta. And lastly, we have some concrete example of Z1 and Z2. And now we are going to do some operations on Z1 and Z2, first multiplying with each other, followed by the complex conjugate. That's the first example, as well as complex conjugating Z1, multiplying complex conjugation of Z2. Concretely, you can actually do this in rectangular form as well, or you prefer polar form, doesn't matter. If you open up this operation, 4 plus 3i multiplied by 2 plus 5i, which is Z1 and Z2, then you will get minus 7 plus 26i. The complex conjugate of this vector changes only the sign at the imaginary part. So she's here. Alright, now Z1 bar multiplied by Z2 bar. So what we realize is that to do this, we take Z1 and perform complex conjugate. So on top is Z1, 4 plus 3i. So Z1 bar means 4 minus 3i. We are taking the complex conjugate of Z1. What about here? This guy is Z2 bar. We take Z2, which is 2 plus 5i. We perform complex conjugate, which is 2 minus 5i. You open up the bracket, and then you will result in this. You notice that this is equals to this, because as we seen in the last example, Z1, Z2 complex conjugate is same as Z1 complex conjugate times Z2 complex conjugate. So this is the identity that we have used, and we have shown that actually it also works. Alright, you can try the different other identities. You will see that the complex conjugate distributes in this following manner through these operations. With that, thank you.